When you look at the stars, you are not touching space, you are traveling through time. Every photon we capture is a message from the past. The moon's light arrived 1.5 seconds ago, the sun's 8 minutes ago. But what if the deepest secrets of the cosmos are written in a language light cannot read? For centuries, we taught ourselves new ways to translate light, colors, spectra, images, and every advance rewrote our cosmic story. This is a story about what we see, what we miss, and what happens when the relationship between observer and matter itself begins to change. There is a wall light cannot pass, a boiling sea of plasma that veiled the universe in its infancy and hid the first heartbeat of creation. We learned to read messengers that cross such barriers, neutrinos, gravitational waves, signals that slip through the veil. By building new ears for the universe, we expanded what seeing can mean, and with it, the questions we dare to ask. What if the missing matter is not missing at all? What if its link to light, its coupling, has shifted so that ordinary matter appears hidden? Enter the Dynamic Cosmic Coupling Model, DCCM, a proposal that the cosmos's visible mass changes how it couples to our instruments, altering what we measure. Here, C of R is a coupling coefficient, a field that modulates how strongly matter interacts with electromagnetic probes as a function of location and velocity. Applied to galaxy rotation curves, DCCM doesn't invent unseen halos. It modifies the apparent response of the mass we already observe, producing a fit that traces small ripples in gas and stars. Those ripples, tiny departures from a smooth rotation, become the fingerprints of a change coupling, not necessarily of exotic particles. The standard picture places unseen mass in a vast halo. It is powerful and predictive, yet there remain tensions and anomalies on small scales. Modified gravity and particle halos each answer parts of the riddle. DCCM offers a different path. Not new gravity, not necessarily new particles, but a change in relation. Part 1. Time Machines of the Eye. How light detectors in biology have always been instruments of time travel. Our senses are filters. We built instruments to extend them, and with each extension, the universe revealed new strata of truth, but also new blind spots. Photon by photon, we decode composition, velocity, and temperature. Spectra are our letters. Doppler shifts help us map motion and mass. Different messengers travel different paths and reach us with different stories. The way they arrive and what they carry shapes the narrative we build. When neutrinos arrive before visible light from a nearby supernova, we learn that sight alone can be deceived. Instruments that hear rather than see changed everything. DCCM is born from that perspective, that different probes may perceive different amounts of matter, not because the matter vanishes, but because its coupling to our probes varies. Imagine the galaxy as a sea where coupling strength rises and falls. In regions of low coupling, ordinary baryons become effectively invisible to electromagnetic measures. The DCCM function is compact. C of r equals x minus v of r over v sub c to the power of n. It depends on local velocities in a characteristic scale, producing a spatially varying veil. Vr is the orbital speed at radius r. Vc is a characteristic velocity scale. N shapes how sharply coupling changes. Together they create a mask over ordinary mass. Switch the coupling and the rotation curve morphs. The visible response of matter changes, not its mass, but its electromagnetic footprint. If coupling varies with environment, then many observations attributed to dark halos might be reinterpreted as differences in how matter meets light. NGC 6503 is an ideal test case. A nearby spiral with high-resolution rotation data and clear gas structure. A laboratory for coupling hypotheses. When we plot observed rotational velocities against radius, Newtonian expectation drops while observed speeds remain higher, a discrepancy traditionally explained by unseen mass. Apply a spatial coupling map and the apparent excess speed can be reproduced using the baryons we actually observe, because their electromagnetic coupling has been modulated. Crucially, the model traces not only the global shape, but the fine structure. The ripples align with gas over densities, giving a direct link between visible matter and the apparent gravitational signal. Building these fits requires high-resolution gas maps, rotation measurements, and careful calibration of the characteristic velocity scale and index. Comparing models is the scientific crucible. Does DCCM explain more anomalies with fewer assumptions, or does it trade one mystery for another? Skepticism is healthy. Extraordinary claims require extraordinary tests. DCCM proposes predictions, and predictions are what science uses to separate ideas from illusion. The path forward is observational. Targeted HI and CO surveys, deep integral field spectroscopy, and multi-messenger correlation to test whether coupling variations mirror the anomalies we see. Part 2, the wall of silence, the opaque dawn that forced us to invent new messengers and rethink what seeing means. Before recombination, photons scattered incessantly off free electrons. Light could not escape. The universe was opaque, and the first moments were obscured. The cosmic microwave background is the fossil light of that era, a snapshot of the first clear surface. But it is not the whole story. Neutrinos and gravitational waves pierce where light cannot, offering complementary views of the early universe's dynamics. Could a coupling field have existed in the primordial plasma, modulating interactions in ways that alter the later distribution of baryons and dark signatures? If coupling played a role early on, its fingerprints might be subtle, slight imprints on acoustic peaks, modified baryon-photon interactions, or unexpected correlations across scales. The cosmic power spectrum is precise. Any model that changes interaction strengths must thread a narrow observational needle to remain viable. DCCM walks that needle by remaining conservative in early universe claims, while focusing its explanatory power on galactic and subgalactic scales. The mathematical core is intentionally simple, an exponential dependence on local velocity normalized by a characteristic scale, shaped by n, but its consequences are broad. Different galaxies may require different characteristic parameters. DCCM is a family of behaviors, not a single universal curve, reflecting the diversity of galactic environments. The test is comparative. Does a coupling map tuned to gas morphology outperform halo fits across a representative population? In NGC 6503, high-resolution HI maps reveal fine structure. When we overlay coupling estimates, the patterns align in ways that invite deeper scrutiny. Residuals, those small mismatches, are the hard currency of model testing. DCCM aims to reduce systematic residuals by tying them to observable baryonic structure. This requires better, deeper surveys, finer spectral resolution, and careful accounting of gas physics and feedback processes. Part 3. Breaking the rules. A look at how DCCM challenges assumptions and what that challenge could mean. Science advances by asking whether we are looking with the right questions. Sometimes the revolution is not a new object, but a new relation. DCCM's workflow is transparent. Observe baryons, infer local coupling from dynamics, predict rotation, and compare. Repeat across samples. Real galaxies are messy. Feedback, inflows, and turbulence complicate the picture. Any coupling model must survive the mess. DCCM predicts signatures, localized spectral decoupling, velocity-dependent emissivity changes, and correlations between gas clumping and apparent mass anomalies. Planned tests include targeted integral field campaigns, cross-correlating HI and CO maps with stellar kinematics, and multi-messenger constraints where available. If coupling reduces electromagnetic visibility, then other messengers, or precise dynamical tracers, may reveal the baryons that light hides. We have seen how light informs, how walls can silence it, and how a changing coupling could recast the missing matter problem as a puzzle of relation rather than substance. Part 4. Vertical time and coupling horizons. Reimagining black holes, horizons, and the dimensions of observability. What if horizons are not only geometric but relational? Boundaries where coupling strength changes so that matter shifts into observationally deeper layers. We call these layers vertical time, a metaphor for degrees of observational coupling. As matter crosses them, its electromagnetic signature can dim without vanishing. An event horizon is a geometric border predicted by relativity. A coupling horizon would be where matter's electromagnetic handshake weakens. Two different languages describing boundaries. In accreting systems, coupling gradients could alter how radiation emerges from the inner flow, changing line profiles, timing signatures, and apparent brightness. Some puzzling spectra and timing anomalies near compact objects may be fertile ground to test these ideas, where coupling and geometry both imprint signals. Theorists caution against quick leaps, yet curiosity compels us to probe. Is there more structure to observability than our standard models allow? Imagine moving not only forward in time, but laterally into layers of coupling. Some views grow thin, Others reveal hidden depth. Observability becomes a coordinate. Testing vertical time ideas demands instruments that can cross linguistic boundaries. Multi-wavelength, high-resolution, and multi-messenger campaigns. From deep HI mapping to coordinated neutrino and gravitational wave follow-up, the blueprint is interdisciplinary, requiring collaboration across observational modes. Part 5. Rewriting the story. What changes if we accept that relation can masquerade as absence? If coupling governs what we detect, then the missing mass is not a ghost to chase, but a relationship to measure, a different map of the same territory. We do not search for mass alone. We search for our relation to it. Changing that relation changes the questions we ask, the instruments we build, and the stories we tell. The dynamic cosmic coupling model is not the final word. It is a lens that reframes anomalies and points to concrete tests. Science advances by trial, error, and the courage to look differently. Whether the universe hides matter in halos, in modified gravity, or in changing couplings, the journey is the same: to refine our questions until nature yields its answer. The truth is not always what we see, but how we choose to look. We are not searching for missing mass. We are searching for our missing relation with matter. Produced by Production Company. Narration by Narrator Name. Research contributions by List Placeholders. For detailed references and data sources, see the companion notes. Behind every graph is a team. Behind every theory, a conversation. Join us in the work of understanding.